What specific problem does your position piece address in the context of generative AI and model collapse? Can you outline the main narratives you are challenging?
My position piece addresses the oversimplified and often mischaracterized narrative surrounding model collapse in generative AI, particularly the belief that training future models on synthetic data will lead to catastrophic performance degradation. I challenge the prevailing notion that model collapse is a singular, dire threat by revealing that the term encompasses at least 8 different definitions of performance degradation, which are inconsistently applied across the literature. Additionally, I argue against the assumption that models are trained solely on synthetic data generated by their predecessors, emphasizing that real and synthetic data accumulate together, which alters the dynamics of model training. Furthermore, I contend that many predictions of model collapse stem from unrealistic experimental setups, and that the most concerning scenarios can be mitigated through standard practices in model development. Ultimately, I advocate for a more nuanced understanding of model collapse that focuses on specific failure modes and the real issues of diversity collapse currently affecting generative models.
How does the proposed method of analyzing model collapse work? Illustrate the step-by-step process you used to identify and categorize different definitions of model collapse in the literature.
The proposed method for analyzing model collapse involves a systematic review of the literature to identify and categorize different definitions of model collapse. First, we hand-annotated 28 prominent research publications on model collapse to determine which papers provide explicit definitions, either mathematically or verbally. Next, we categorized the definitions into 8 distinct types based on their notions of performance degradation, such as catastrophic increase of population risk and disappearance of real tail data. We also noted instances where papers used multiple definitions, leading to inconsistencies and contradictions. Finally, we emphasized the importance of definitional rigor to enhance clarity and drive progress in understanding model collapse, suggesting that researchers should adhere to clearly stated definitions to avoid confusion and misinterpretation of results.
Could you provide a concrete example of how one of the definitions of model collapse manifests in a generative model's performance? Walk through this example to clarify your explanation.
One concrete example of model collapse is the disappearance of real tail data, also referred to as coverage collapse. This definition manifests when a generative model progressively loses the ability to represent examples from the tail of the data distribution, leading to models that can handle only common cases but fail on rare ones. For instance, if a generative model is trained primarily on synthetic data that lacks diversity, it may produce outputs that do not include rare but important instances, such as specific dialects in language models or uncommon medical conditions in healthcare applications. As a result, while the model may perform well on average population risk, it could exhibit significant performance degradation in edge cases tail risk, ultimately failing to generalize effectively in real-world scenarios. This phenomenon highlights the critical need for maintaining a diverse dataset that includes both common and rare examples to ensure robust model performance across the entire data distribution.
What are the practical implications of your findings regarding model collapse for AI development practices? How do these insights influence the design and training of future generative models?
The findings regarding model collapse suggest that AI development practices should prioritize a realistic understanding of data propagation and the definitions of model collapse. Specifically, the paper emphasizes that models should not be trained solely on synthetic data generated by their predecessors, as this could lead to misleading conclusions about performance degradation. Instead, it advocates for the accumulation of both real and synthetic data, which can mitigate catastrophic increases in population risk and prevent significant performance degradation. Furthermore, the insights highlight the importance of maintaining a diverse dataset to avoid loss of real tail data and mode collapse, which disproportionately affects marginalized groups. Overall, These findings encourage AI developers to adopt best practices in dataset curation and model training that reflect realistic conditions, thereby enhancing the robustness and effectiveness of future generative models.
In your paper, how did you validate your claims about the inaccuracies in the prevailing narratives around model collapse? What types of metrics or benchmarks did you use to assess the impact of synthetic data on model performance?
In our paper, we validated our claims about the inaccuracies in the prevailing narratives around model collapse by conducting a thorough analysis of existing literature, hand-annotating 28 prominent research publications to identify and categorize the various definitions of model collapse. We highlighted that many papers lack explicit definitions and often use multiple definitions inconsistently, leading to confusion and misinterpretation of results. To assess the impact of synthetic data on model performance, we employed metrics such as population risk, defined as the expected loss over the entire real data distribution, and tail risk, which focuses on the expected loss conditioned on tail events. We also examined specific failure modes, such as catastrophic increases in population risk and the disappearance of real tail data, to illustrate how different definitions can lead to varying conclusions about model performance degradation. By synthesizing these findings, we argued that the most widely stated collapse scenarios can be avoided through standard practices in model development and dataset curation.
What are some of the key limitations of your analysis, particularly regarding the assumptions made about data propagation and the implications for real-world applications of generative models?
Some key limitations of our analysis stem from the assumptions made about data propagation, particularly the unrealistic notion that all existing data are deleted after each model fitting iteration. This replace paradigm contrasts with the more realistic accumulate approach, where synthetic data accumulates alongside real data, which significantly alters the expected behavior of population risk. Our analysis suggests that under realistic conditions, population risk does not diverge catastrophically, but this relies on the assumption that the proportion of real data remains sufficiently high. Additionally, while we acknowledge the potential loss of real tail data and modes, the exact extent and speed of this loss remain unclear, which complicates the implications for real-world applications of generative models. Therefore, our findings may not fully capture the nuanced dynamics of model collapse in practical settings, emphasizing the need for further research into how these assumptions affect the performance and reliability of generative models in real-world scenarios.